Okay, welcome to the virtual Atwood machine lab. All right, an Atwood machine is what you see in front of you, and it consists of a couple of pulley wheels with a string draped over them and different sized masses attached to each end of this string. And what happens is uh, someone not in the picture would be holding the string to prevent it from moving. And as you might guess, the heavier mass it will move down and the lighter mass will move up when released. So when I press the start button, it simulates a person releasing the weights, which are being held in place right now, and then it starts to accelerate. If we reset it and we the adjust the masses so that there's only a slight difference between them, they're almost balanced, and we can actually see that acceleration a little bit slower. And there you go. So what we're going to do in this lab is figure out how to calculate the acceleration, how to predict it using mathematics and physics, and then how to check it using data that is being recorded by the vernier motion sensor. So the sensor is recording the position and the time of this mass right here. So right now, this distance is considered 0. So we're calling that 0, even though it's not quite touching the sensor. It's kind of calibrated to be 0. And as the mass moves away, the distance or position is increasing. So that's why over time we see that distance increasing, and that's what's reflected on this graph. We can see as time goes on, the position is getting further and further away at an increasing rate, right? That's because the object is accelerating. To check the acceleration, we can also use the velocity values recorded by the machine to calculate the velocity of that mass moving away from the vernier sensor. And as you can see, the velocity starts at 0, so it's not moving, and then the velocity keeps getting faster and faster and faster, increasing at a linear fashion, which means the acceleration is constant. So we can calculate the acceleration by calculating the slope of this graph. So let's go ahead and get started. So first thing I want to do is understand what are the forces at play? How do you calculate the acceleration of this machine? So over here, we have a picture of the Atwood machine, and the only forces we care about are the external forces. We don't care about internal forces. Internal forces never cause the system to accelerate. We care about external forces. The first question actually is, what is our system? So we need to define our system, and I'm going to define the system that's accelerating is the masses plus the string. Everything else is outside of the system. So everything else that's touching the string or touching the masses or not touching, like gravity, those are external forces to the system. So if I redraw the mass and the string and I ignore everything else and I start to label forces on the system, the first force you can always label is the force due to gravity. And this mass will also have a gravitational force pulling down, right? So those are my non-contact forces. We'll consider the mass of the string to be negligible. But now the contact forces. What is the mass in contact with? Well, just the string, and that's part of the system. So what are the external forces that the string and mass are in contact with? Well, that's just the wheel. Right here, right along this edge and right along this edge, the string is in contact with the wheel. So the truth is there are some external forces pushing the string up right here and right here. Otherwise, there would be no vertical force to counter these forces right here, and the whole system would start to move downward. It would just accelerate down and collapse towards the ground. So this is the wheel pushing back up. So I'm going to write F wheel, right? And the wheel's also pushing the string out to the side, okay? But these forces don't cause the system to accelerate, all right? The motion of the string, when I let go, it's going to move in this direction right here, right? This is the direction of motion of the system. So this is, normally we would say it accelerates in the X direction or accelerates in the Y direction. With an Atwood's machine, you define the direction of acceleration by drawing the path that the masses and string move along. So those green arrows are the direction of acceleration. Okay. So the question is, which forces are causing the system to accelerate or causing the system to decelerate, to slow down? Well, these wheel forces right here, sorry, let me use red. Those wheel forces are perpendicular, right? This wheel force is perpendicular to the string in the direction of motion of the string, right? Perpendicular. So it's not causing the string to move to the left at that point. Similar to this force right here is perpendicular to the direction of motion, so it's not causing acceleration. Same thing could be said about this force right here being perpendicular to the upward motion, and this force right here on the left being perpendicular to the downwards motion. Those forces are not causing the system to accelerate. However, if we look at this force due to gravity, the direction of that arrow is downward, and that is the direction of motion, right, on that left side. If we look at the force of gravity on the right side, it's downward, and it's exactly opposite the direction of motion, so it is acting to slow the system down. So we actually only have two forces that are external to the system that are causing the system to accelerate, and those are the forces due to gravity. So we'll say Fg mass 1 and Fg of mass 2. That's it. So those are the forces. And the formula we're going to use to calculate the acceleration is this right here. The sum of all forces is equal to the mass times the acceleration. The trick is, right, what is the sum of all forces? In this case, it's just going to be FGM1 plus FGM2, because those are all of our forces. Noting that Fg of M2 is going to be negative because it's acting opposite the direction of motion. So just keep in mind that this term right here needs to be negative, right? Whereas this term needs to be positive because it's causing the system to accelerate in a positive way. Now, the mass is the mass of the system. This is an equation for the entire system. We're modeling all the forces on the mass string mass system. So mass would be just M1 plus M2. Right? So we need to make sure we include the mass of the entire system, and that will help us calculate the acceleration of both pieces. They accelerate at the exact same rate because they are attached together by the same string. So that is the setup for our calculations.